Welcome to our deep dive into image analysis and histotechnology, a crucial skill for future lab leaders. We'll explore what we quantify in tissue samples and, more importantly, why it matters for patient care. This lecture will help you understand the limitations of visual assessment and the power of digital tools. We'll cover the problem with the eyeball estimate using a clinical example, define the labeling index, and conceptually walk through the 4 steps of software analysis. We'll also land on the hard caution that a precise wrong number is dangerous, making the visual overlay check non-negotiable. So let's dive in. When we look at a stained tissue section, our eyes try to make sense of the patterns, but this can be highly subjective. Consider Ki67, a common proliferation marker. Visually estimating its expression can lead to significant variability between observers. This variability isn't just an academic exercise. It has real consequences for patient treatment. For example, a 5% difference in a Ki67 score can literally be the difference between a patient receiving aggressive chemotherapy or not. So how do we move beyond the subjective eyeball estimate to something more reliable? We need a standardized, quantifiable approach. So what exactly are we trying to quantify when we look at these slides? We're often interested in the proportion of cells expressing a particular marker, like Ki67. This isn't about counting every single cell, but rather understanding the overall cellular activity. We're moving from a qualitative, is it positive or negative, to a quantitative, how positive is it? This shift allows for more precise diagnostic and prognostic information. This precision can help us overcome the variability we just saw in visual assessments. The labeling index is our key metric here. It's simply the percentage of positive cells out of the total number of cells. For example, a Ki67 labeling index of 20% means 20% of the cells are actively proliferating. This single number provides a powerful, objective measure of cellular activity. Visualizing this index helps us understand the extent of proliferation in a tumor, which can guide treatment decisions. Now let's look at how software helps us achieve this precise quantification. The first step in software-based image analysis is color deconvolution, which separates the different stains in a tissue section. Imagine a slide stained with hematoxylin and DAB. The software mathematically unmixes these colors. This is hard because standard RGB cameras don't naturally separate DAB brown from hematoxylin blue. It requires complex optical density math. This allows us to analyze each stain independently, ensuring that our measurements are specific to the marker of interest. This initial separation is crucial for accurate downstream analysis. Now that we've separated the colors, the software moves to detection, which is where the program identifies individual cells and their nuclei. This is like teaching a computer to see each distinct object in a crowd. The software uses complex algorithms to find the boundaries of each cell, making sure not to count overlapping cells as one. This step is crucial because accurate detection directly impacts the final count. If the software misses cells or counts one cell multiple times, our index will be off. Remember, standard RGB cameras don't naturally separate DAB brown from hematoxylin blue. It requires optical density math, which is why color deconvolution is so hard. So we're building a foundation of individual cell recognition here, which sets us up for the next step of classifying them. After detection, we move to thresholding, which is all about classifying those detected cells. Here, the software applies a specific intensity threshold to determine if a nucleus is positive or negative for the stain. Think of it as setting a brightness level. Anything above this level is positive, anything below is negative. This step is where we decide what counts as a stained cell. The challenge is that staining intensity can vary, so setting the right threshold is critical for accurate results. Pre-analytical variables like overfixation in formalin or thick microtomy sections can artificially darken the tissue and ruin the threshold. A threshold set too high might miss weakly stained positive cells, while one set too low could include negative cells. This classification is what allows us to differentiate between the cells we care about and those we don't. Once we've detected and classified all the cells, the software moves to reporting the index. This is the final calculation where the program divides the number of positive cells by the total number of cells. The result is our labeling index, a precise numerical value. This index gives us a quantitative measure of the proliferation rate, moving us far beyond a subjective eyeball estimate. It's the culmination of all the previous steps, providing a standardized and reproducible result. This numerical output is what clinicians use to make informed decisions. For example, the software might accidentally count dark blue, dense lymphocytes as positive tumor cells if the threshold is bad, leading to a falsely elevated labeling index. This is why we must always verify the results. So why does all this rigor matter? Because a precise wrong number is far more dangerous than a vague estimate. We're dealing with patient diagnoses here, and an inaccurate index can lead to incorrect treatment. For instance, a 5% difference in a Ki-67 score can be the difference between a patient receiving aggressive chemotherapy or not. This isn't just an academic exercise. It has real-world consequences. The detailed steps of color deconvolution, detection, thresholding, and reporting ensure that our numbers are not only precise, but also accurate. This meticulous process underpins the reliability of our diagnostic tools. It's about ensuring the integrity of the data that guides clinical decisions. We've talked about the incredible rigor of digital image analysis, but here's the caution that truly matters most. A precise wrong number is far more dangerous than a vague estimate. Your quick eyeball estimate, while subjective, at least comes with an implicit understanding of its imprecision. But when you get a number from software, there's a tendency to trust it implicitly, even if it's fundamentally flawed. This is especially true with something like Ki-67, where a mere 5% difference in the score can be the difference between a patient receiving, again, aggressive chemotherapy or not. So while the software gives you a number, you must always question its accuracy. And this brings us to the non-negotiable step in digital image analysis, which we'll discuss next. So this is the critical step you absolutely cannot skip. Always check the overlay. The software provides a visual overlay of its analysis, showing you exactly what it detected and how it classified each cell. This is your chance to visually confirm that the software's interpretation aligns with biological reality. For example, if your thresholding is off due to pre-analytical variables like overfixation, the software might accidentally count dark blue, dense lymphocytes as positive tumor cells, which again is leading to a falsely elevated labeling index. You're looking for correctly identified nuclei, accurate thresholding of positive staining, and proper exclusion of artifacts. If the overlay looks wrong, the number is wrong, no matter how many decimal places it has. This visual check is your final quality control, ensuring the precision you gain from automation is also accurate. It's the bridge between the digital output and your expert biological understanding, and it's what we'll summarize next. So to summarize, digital image analysis offers incredible precision, but that precision is only valuable if it's accurate. We've seen how the eyeball estimate, while quick, lacks the consistency needed for clinical decisions. The labeling index provides a standardized quantitative measure, but its reliability hinges on proper software application. Remember the 4 steps: color deconvolution to separate stains, which is hard because standard RGB cameras don't naturally separate that dab brown from hematoxylin blue, and also requires optical density math. Detection to find the cells, thresholding to define positivity, which can be ruined by pre-analytical values like thick microtomy sections, and reporting to give you the numbers. But above all, never forget the caution. A precise wrong number is dangerous. Always, always check that visual overlay. Your ability to critically evaluate the software's output is paramount. Now, let's move on to our hands-on lab where we'll apply these principles.